So now I'm going to talk on cylindrical coordinates. And this is going to be a short lecture, in part because cylindrical coordinates are not really anything different than what we did with polar coordinates. We're just adding a z, and this z is the same z you're used to in rectangular coordinates. So in cylindrical coordinates, just like we had in polar coordinates, we're going to have an r, which is going to be the square root of x squared plus y squared if we are trying to convert, say, from rectangular coordinates to polar coordinates or cylindrical coordinates. So it's r is equal to the square root of x squared plus y squared. Theta is the arctangent of y over x. This is not necessarily a great thing to use because you got to keep also in mind where x and y are in the plane. If x and y are in the first quadrant, this formula works fine. If x and y are in the third quadrant, then x and y are both negative, and so y over x would be positive, and the arctangent would be between 0 and pi halves. But if x and y are in the third quadrant, the angle we want, the theta, should be between pi and 3 pi over 2. So you can't always use this, but it gives you a rough idea of what's going on. If you figure out the arctangent and you know which quadrant y and x are in, then you can determine what theta is from this information. Z, again, is just going to be the usual z we're used to in rectangular coordinates. And this would tell us what r, theta, and z are in terms of x and y. So if we're trying to convert from one system to another, if we're given r and theta and z, and we want to know what x and y are, x is r cosine of theta, y is r sine of theta. Again, these are things we saw in polar coordinates. They haven't changed. And the z, of course, is just going to be z. So if you're given the cylindrical coordinates, you have a z, it's the same z in rectangular coordinates. Now, in general, I would prefer to use this to figure out what theta is. So figure out first what r is from this formula if you're given x, y, and z. And then you know x, y, and r. So if you're given x, y, and z, you know r now because you figured this out. And then you'll know what cosine of theta and sine theta are. Cosine of theta will be x over the r you computed, and sine theta will be y over the r you computed. And there's only going to be one theta between 0 and 2 pi that has those values for cosine of theta and sine theta, and that will be the theta that you want. So this tells you what we want to do with our solid. We're breaking up into small pieces like this. Instead of rectangular boxes, you can see they're almost like boxes, but the bottoms look like these little pieces of a sector that we talked about before in polar coordinates, and then we're adding some thickness to them. So this thickness is delta z. So for finding the volume of this, we're just going to take the area of the base times delta z. The area of base we computed before. This was delta r, the change in the angle we called delta theta, and we said that delta A, the area of this, was equal to an r roughly in about this distance apart. This will be small, so whatever r is there, delta r, delta theta. So this is what we had before, r delta theta roughly here for the area of this. And now we're adding some thickness, so we want to multiply this by delta z, and that's going to give us the volume of this piece. And so we want to imagine adding up lots of volumes or pieces of volume like this. And then what we're going to get in a limit as the number of pieces go to infinity and the dimensions go to 0 of these boxes is a triple integral, dv, and that dv is going to be the same thing as r dz dr d theta. So if we have a function in here, you can throw that in, but the triple integral is going to be a triple integral with respect to zr and theta, where we have an extra r in here for the delta v, becomes a dv again, r dz dr d theta. So we get an extra r there, just like we did in polar coordinates. So this is just telling us if we have a triple integral given to us in terms of x, y, and z, and we want to convert it to a triple integral in terms of ZR and theta, so a triple integral in cylindrical coordinates, then what we should do is to replace the x with r cosine theta, the y with r sine theta, the z stays the same, and the dv, which here would be dx dy dz, is going to become r dz dr d theta. So we replace the dx dy dz with r dz dr d theta. So unlike the dv for rectangular coordinates, which I can order these dx, dy, dz in any order, you can do the same thing here, but I will typically just use dz, dr, d theta. So typically dz, dr, d theta does what you want. This is telling you how to set up a triple integral in cylindrical coordinates. And again, this is the opposite of what I would really do. I would do steps two first here. But all this is doing, saying, is take the shadow of your solid in the xy plane, and then set up the double integral in the xy plane like you would if you were doing a double integral in polar coordinates. You would go ahead and figure out the range on theta. So theta is between two angles here, and then r is going from the closest curve to the origin to the furthest curve from the origin. And that sets up your double integral in polar coordinates, but it's also for cylindrical coordinates. And z goes from the bottom surface to the top surface. The bottom surface in this case is g1 of r theta, and the top surface is g2 of r theta. So it's going from the bottom to the top. And that's the same thing it does in rectangular coordinates. You want to go from the bottom to the top. You're going in the positive z direction. And you just go from the first thing you hit to the last thing you hit. So that's pretty much it. So let me just do an example here. So we want to find the volume of this solid that's bounded by these paraboloids, z equals x squared plus y squared. That's the bottom one here. And the top one is z equals 36 minus 3x squared minus 3y squared. So we have these two paraboloids. We want to know the volume of this, and we're going to set this up first in cylindrical coordinates. And to do that, well, first, why would that make some sense? Well, the shadow you can see in the xy plane is just going to looks like it's a circle. Let's figure out what that shadow is. So that shadow is where these two paraboloids intersect, and it's going to be that what looks like a circle as the shadow. Let's calculate that. So if I want to know where these intersect, I know that the points x, y, and z have to satisfy both of these where they intersect. And so x squared plus y squared will equal 36 minus 3x squared minus 3y squared. So I just put that down here. I brought the 3x squared and 3y squared over. So I have 4x squared plus 4y squared now equals 36. So 3x squared and 3y squared with the extra x squared plus y squared here. And so I divide by 4, and I get x squared plus y squared equals 9. So that's describing the x and y on this intersection of these two paraboloids. The z, if you want to know what's happening with z, well, z equals x squared plus y squared. So z would be 9 here. You could also plug into here. You have 3 times x squared plus y squared in parentheses, and the 3 times x squared plus y squared would be 27. So you have 36 minus 27, or 9 again. So z equals 9 no matter which one we plug it into. The x squared plus y squared equals 9, and z also equals 9. So z equals 9 is the plane. Z equals 9 cuts these paraboloids exactly where they intersect in the circle where x squared plus y squared equals 9. So I want to think of that circle in the xy plane. It's just a circle centered at the origin of radius 3, and I want to set up the integral. So again, we're going to use polar coordinates in the xy plane to set this up and then throw in a z here. So in polar coordinates, theta would be going from 0 to 2 pi, you're going all the way around this circle, and r would be going from 0 to 3 because it's a circle of radius 3. So that's all I did for these outer two integrals. I'm thinking of this again in the xy plane and writing the double integral in terms of r and theta. Theta goes from 0 to 2 pi, r goes from 0 to 3 for this circle in the xy plane. And now I want to go from the bottom to the top. I want to think of going in the positive z direction, and the first thing I hit is this paraboloid. So, and then the last thing I hit is this paraboloid. Well, which one's on the bottom here? Well, this one goes through the origin, so that's the one that's on the bottom. This one on the z-axis when x and y are 0 is 36. So that's up here. And the bottom one is z equals x squared plus y squared. And we have to write that in polar coordinates or cylindrical coordinates where x squared plus y squared is r squared. So we get z equals r squared. And so that's on the bottom. That's this paraboloid, and this paraboloid is the top one. And here again, if we have x squared plus y squared equal to r squared, this will be 36 minus 3r squared. So that's where this comes from. That's just rewriting this in polar coordinates or cylindrical coordinates where x squared plus y squared is r squared. So we get 36 minus 3r squared for the top one. Z equals that in terms of r and theta. So that's really all there is to setting this up. We can evaluate it now. We integrate r as a constant, z, so we just get an r times z here, and we're evaluating z from r squared to 36 minus 3r squared. So the r I just kept here, but the z going from here to here, I take 36 minus 3r squared minus r squared, and that gives me 36 minus 4r squared. So now I want to integrate this. So I have 36r minus 4r cubed. So 36r, when we integrate it, is going to give us 18r squared. Okay, so the r becomes r squared over 2 times 36. You get 18r squared. When I integrate this, it's 4r cubed, remember. So 4r cubed is just going to be 4 times r to the fourth over 4. So it's just r to the fourth. So we're getting 18r squared and a minus r to the fourth here. So that's what we get when we integrate 36r minus 4r cubed. And we want to evaluate this from r equals 0 to 3. Now, at 0, this is going to be 0. If we plug in 3, we can maybe be a little bit careful here. This is 2 times 9 again. So it's 2 times 81, and this is 81. So 2 times 81 minus 81, we're just going to get 81 there. So that becomes 81 when we evaluate that. So I have 81, and then I'm integrating from 0 to 2 pi d theta. So I'm just going to get 2 pi times 81, or 162 pi. So 162